Hey, students, I just got a great question about it's number 33. It's from chapter 23, but it's from the university physics, and that would make chapter 16. And anyways, it's a bit of an interesting, challenging problem, and of course, it has the calculus with it. And it says this: it says, show that the magnetic field, a distance r, from the axis of two circular parallel plates produced by placing charge q with a function of time on the plates is given by this equation. So here's kind of the argument here is that, and I printed this picture kind of helpful. It shows some current coming in and beginning to charge up this plate, which of course through an electric field would chase off negatives. And so here's our capacitor. Now, it doesn't really show, and so I thought I would add to the rest of the picture is, maybe we would have a battery over here, and then maybe also some kind of switch. So the idea is I'll put S for switch and V for voltage. When you close this switch, current begins to flow. And as we learned with capacitors earlier on, this would begin to charge up. And in fact, we had an equation for the charge on the capacitor, and for that matter also the voltage, is some maximum value. And then it was 1 minus e to the minus t over tau, the RC time constant. Now, I guess in my picture, I should have maybe put a resistor here. So this is our battery and our R, and then here's the capacitor, and it building up charge. And when we did capacitors a couple chapters ago, our focus was just on the fact that they charge up and the rate at which they charged with this time constant, this what we called an RC time constant. And all that is very true. And so I just wanted to remind you of that, because also I wanted to remind you, going back just one chapter, is we learned that if you just had a wire, and so let's just forget the capacitor here for a moment, but just a wire, and if it's a long straight wire, we learned that it would create a magnetic field given by this equation, where I is the current. And that's what this picture is trying to illustrate. You can see the current going down. So if I take my right hand and point my thumb down, the magnetic field would kind of be this brown line, and this would be the circle around it, and they're showing the field at this point. And so there'd be a field making a circle around it given by this formula. So it would depend on how much current, and it would depend upon, of course, the distance away. And so what this problem is asking you to do is to kind of put those thoughts together here and say, now, what would you do if, and maybe I'll grab a blue color, what if instead of talking about this circle here, this dotted line in kind of a burnt yellow, that would be given by this, what if we kind of imagine us doing that same thing kind of around the belly of the capacitor? And in that sense, you would say, well, there's not really a current going through here. There really is a charge that is building up. But that building up of charge really is the current. And that's what this problem is kind of asking you to do. This problem is trying to say that if you kind of take what we already learned from Ampere's law about a magnetic field, and you then, and I'll leave this alone here, take the definition of the current, which is how charge is changing with time. And of course, in this book, then you change it in the limit that time goes to 0, so we can call it a calculus one, we would have this mu naught over this 2 pi r, and then we would have a dq over a dt. And that is what we're after. So there's not a whole lot of deep steps to do this problem, other than maybe kind of pointing out that what we're really saying here is the magnetic field doesn't really know or change or matter whether or not we're looking at it where there's current and there's really kind of a moving charge, or someplace that is kind of in the belly of the capacitor where you might say, well, there's not really a charge going through here. What happens is a positive builds up and then chases a negative away through this electric field. But what you would be saying then is there still is a flow or a changing of charge. So that's really what they're asking to do, is just to change this I into a dq dt. Nothing big. And I guess we don't even really need this, but what we could do if we wanted to go one step further is actually then put this in and say we know how the charge changes with time. It's going to be some maximum charge and then has this rate of change. It's probably the best way. So then we can actually go through the math and take the derivative. And I thought we were going to have to go that far, but we don't have to go that far. It's just right here. It's just kind of a continuation of saying take the charge, or take the current and think about what it is, which is a change of charge, and apply your calculus. That's what this problem is centered around. But the visualization is then, and this was Maxwell's argument, that the field would be the same, whether or not I'm kind of drawing a loop where there's actually real current, or a loop that I'm going around a belly and there's not really current, but what there is a changing charge on the plates. And that's what this is. All right. Hope that helps. Take care.